Okay, so in our first lecture, we're going to look at orthographic views. These are the views that we use to describe graphically um, a three-dimensional object on a two-dimensional surface. Okay, so really the need for orthographic views came about because when engineers or designers, or for that matter, architects, are trying to describe three-dimensional objects, we run into a problem in that the way that we are left to communicate our design ideas is on a two-dimensional surface such as paper. Okay, and so we have a problem in trying to figure out how to describe our three-dimensional object on that two-dimensional surface. And orthographic views or orthographic viewing is the way that was developed to help us to overcome this this problem. Okay. So orthographic projection is the name associated with taking a three-dimensional object and displaying it two-dimensionally. Okay, so what we have here is an object, a three-dimensional object, and we have a viewer that's looking at what we might call the front view of this object, and we can see the arrow indicates his line of sight. And when the person views this object, looking at it directly onto the front view like this, what they're going to see would be this two-dimensional view of the front view. All right, so this is what we would call an orthographic projection of the front view. All right, and so orthographic projection is this way of drawing the views of an object using what are called perpendicular projectors from the object onto a point of projection. Okay, now we can't see the projectors or the point of projection here. We'll see that in a later slide. But right now, we're just interested in understanding how we view a three-dimensional object to generate this orthographic view. Now, it's important if you wanted to do this yourself at home, you can pick up any object and view it, hold it up so that you're looking at kind of a front view of the object. But in order to overcome what naturally gives us a perspective view, that is to say, in order to overcome our binocular vision, you need to close one eye. Okay, so in order to generate this two-dimensional view, if you're trying this out at home, make sure that you close one eye so that you can see the object without any perspective or vanishing point kind of situation. Okay, so how do we view the object when we want to look at different sides or different surfaces? Well, we rotate the object. Okay, so now this is what we call a third angle projection. This is the type of projection that we use in the United States. In most of the other countries of the world and in Europe, they use what's called first angle projection, which is different than this. Okay, but this is what's used in the United States. This is called third angle projection. And what we have, in order to generate the top view, what we do is we take the object and we hold it like we did for our front view, and we rotate it so that we're looking at the top of the object, and then we have our top view. We do the same thing when we look at the right side view. We take our object from the front view and we rotate it towards the right so that we then have our right side view. So this is how the views are created or are viewed, the different sides of the object. We just rotate the object in our mind to create the front, top, and right side view. And we could also do the same for a left view, a bottom view, or a back view. Okay. Now, we talked earlier about this plane of projection and the projectors. So what we're talking about here is the plane of projection. Think of it as a glass wall, okay? And that glass surface is placed in between our eye and the object. And the glass surface is oriented so that it's parallel to some major surfaces, okay? So in this case, the plane of projection is parallel to this vertical surface, and looks like this surface right here in the front. Okay. Then we have these imaginary projectors, and the projectors, you can see that they come from each edge or corner of the object out, and they move forward to strike the plane of projection. Okay, so for each corner, the projectors come forward and they stop at the plane of projection. And what happens is when we trace all of these projector endpoints around on the glass surface, we end up with a tracing of the, in this case, the front view of the object. And so that's the idea behind the projection of the object onto a projection plane using the projectors. It's important to note that the projection plane is always parallel to a major surface, okay? And the projectors are always perpendicular to the projection plane. This way we avoid a perspective view and we get a true two-dimensional view of the object. So when we put 6 of those projection planes together and we surround the object, that's when we have our glass box, okay? And if we use the same idea of projectors and projection plane and tracing the surface out, what we end up with is a front view that's traced on the front projection plane, a right side view where the projectors come across here. You can see some of the projectors, and they trace out a right side view on the right projection plane. We have the same thing with a top view. All right, we have projectors going up, and we can trace out the top view of the object. And it's hard to see here, but we would have a left side view, we would have a back view, and we would also have a bottom view. So we would have 6 views that we could trace out onto the 6-sided glass box with our object suspended in the middle, magically somehow. Then what do we do with the glass box? Well, we unfold it. All right, and this is how we get our alignment of our orthographic views, which is a very, very important, very critical thing, the alignment of the views. So it's not just sufficient to have the views like this, right, in a glass box, because the glass box is 3-dimensional. That doesn't help us. We need to get it into a 2-dimensional surface. And so we unfold the glass box. And as we unfold the glass box, we have these hinges right here and right here. And as we bring the top view projection plane up and rotate it up, this alignment occurs naturally. So this edge right here is naturally aligned with the edge in the top view. Same right here. This edge is aligned right there. Same with the right side view. So this bottom edge is aligned. It comes around the hinge and it goes down here. And the top surface, likewise, is aligned. It comes to the hinge and then banks around there. So when we unfold the glass box, we end up with, in this case, 6 regular views or 6 standard views that are all 2-dimensional. They all show different surfaces or different sides of the object, and they're all aligned between them. Okay. This is a little animation that kind of shows that process. So you can see we're basically tracing out the surfaces onto the glass box, and then we unfold it, and we have our 6 regular views. All right. So obviously this is a mental exercise. We don't actually, surround an object with glass boxes and stuff, but this is where the view alignment comes from, where it's developed from. So as we just showed in the last video, we have our 6 standard views, okay? Our front view and our top view, our right side view, which is going to be to the right of the front view, and our bottom view, which is below the front view, our left side view, and then somewhere the rear view could either be developed from the left side or to the left of the left side, or we could put it over here to the right side view, or in fact we could, notice we can get different arrangements of the views. What's important to note, there's a few things that are important to note here. The top view and the bottom view are basically mirror images, but they have different hidden lines, right? So in the top view, because we see this edge right here, this edge is visible. But in the bottom view, because this edge is below the bottom surface, that is represented with a hidden line. So with the right side view and the left side view, they are in fact true mirror images, because there's no surfaces that are occluded or hidden in that's not shown in one of the other views. And the rear view is, like the top and bottom view, a mirror image with some edges transposed from visible to hidden. Okay. Note, though, the alignment of the views. This is very critical. The views always must align. So we have an edge coming down here. In fact, this edge in the top view is this edge in the front view, is this edge in the bottom view. So the views align because we're talking about the same edge. The bottom surface here is this bottom surface, is the same thing here, and is the same thing here. Okay. Now, we often, we don't need to show 6 views, and it's rare that you would actually have 6 views on a drawing, because that's overkill, basically. There's a lot of redundant dimensions in here. So we typically have 3 regular views, whether they are the front, top, and right side view, or the front, top, and left side view, or the front, bottom, and left side view. It doesn't matter. That is more aligned with the exact geometry of the object. But what's critical is to understand that in 3 views, we have all the dimensions that we need. Okay, so let's look at this. So if we say this dimension, let's start from the corner right here. All right. And let's say that to the right is the x direction, and to and up is the z direction. And from this same corner going forward is the y direction, right? So we have x, z, and y. So in the front view, we have x and z. In the right side view here, we have y and z. In the top view, we have y and x. So in our 3 dimensions, right, for a 3-dimensional object, we have x, y, and z. In the front view, we have x and z. In the right side view, we have y and z. And in the top view, we have x and y. So we actually have every possible coupling of our 3 dimensions. And that's why 3 views is really all you need to show most simple 3-dimensional objects. Obviously, for more complex objects, then we have to, have different views, auxiliary views, or maybe, we have a 4th or a 5th view. But generally speaking, the 3 regular views here are sufficient to show every permutation of a pair of the x, y, and z axis. Okay, so we talked a little about the standard arrangement of views. It's important to understand that with the views, we want to try to show them in the normal or natural orientation of the object. So if we were going to do the 6 views of a car, we would show the car with its wheels down. Okay, we wouldn't, and we do that with other objects as well. If the object is supposed to be oriented in such a way in a machine or mechanism, then for the most part, we want to show it that way in at least one of the views in the front view. Okay. Dimensions, if we have the views aligned properly, dimensions will always transfer between views. So I'd like for you to look at figure B, right? So this dimension, D1, is this dimension right here, D1. That edge, basically, we're looking at the point view of an edge, is shown right here in what we might call the edge view. So this edge is the same as that right there. So D1 is the same, D2 is the same right there. This surface right here, what's labeled A, is shown right here as an edge. So this surface is shown as an edge in the top view and shown as an edge in the right side view. Okay. It's not always necessary to show multiple views, right? So we talked about the 6 standard views. We also talked about the 3 regular views. But for simple objects, for objects that are cylindrical or have a uniform thickness, right? Oftentimes we can get away with one view. So in this case, we have a single view of a shim, right? And we note the thickness right here, so it's 1/4 of a millimeter thick, right? In this object, we have a cylindrical object, right? And so we can get away with just showing, this is actually a square end, but we have a diameter here and a diameter here. So again, we only need one view. We don't need a circular view to show all this because this is descriptive enough. So we want to understand that we don't want to show more views than we need, right? We want to be efficient. We don't want to try to over-describe things because oftentimes that introduces error. It introduces confusion, okay? It's a poor communication tool. So a sketch or drawing should only contain the views needed to clearly and completely describe the object. Choose the views that show the shape most clearly, have the fewest hidden lines, and show the object in a typical, stable, or operating position. The main view that we want to focus on is really the front view, right? So pick your front view properly. Pick your front view well. A view that is going to describe the object the best compared to all the other views, and then decide whether you want a top view or a bottom view, a right view or a left view, or whatever other views you need based on the geometry that you need to describe. Okay, so how we unfold the glass box is kind of dependent on the geometry and some other circumstances. So here we have a unfolding of the glass box where the hinge is between, if we call this the front view, the hinge is between the front view and the right side view. And you can see what happens here is we have the side view, the right side view unfolds, and it's really close to the title block, right? And then we have a lot of wasted space up here. And so it might be better to show, to rearrange the views. Actually, we're not rearranging the views. What we're doing is we're moving the hinge. So instead of the hinge being here, we move the hinge up here. It's still the same view, but notice that it's rotated slightly. It still must align. But now we've taken up all this wasted space here, and we've moved our object away from the title block here. Now, I think I talked a little bit about the different types of projection. There's basically third angle projection and first angle projection. First angle projection is used in Europe. Third angle projection is the method used in the United States. And in this method, the third angle projection, the walls of the box are hinged and unfold the views outward around the front view. All right, so the object is placed inside the glass box and the walls or the glass box unfolds around the front view. Okay, so this gives us our standard third angle projection. Here we can see that here, this is the first angle projection. Okay, so notice in this that the object is placed in front and we're tracing onto the back surface. So the tracing is done inside the glass box. That's important. In the third angle projection, we trace the views on the outside of the glass box. In the first angle projection, the object is traced on the glass surfaces on the inside Okay, so the front view is shown here. The right side view is actually to the left of the object. The top view is below the object. Now, this is confusing when you're used to third angle projection, and don't worry, we're not going to do any first angle projection drawings in here, but I can tell you, I did an internship one summer when I was at the University of Florida, and I went to Finland and worked for a large paper machinery company, and the first thing that they had me do was to edit some drawings and do some different editing for their paper drawings. And I did not know that there even was a thing called first angle projection. And so when they gave me the drawings and I noticed that here's the front view, but the right side view is on this side and the top view is down below, I thought that everything was goofy. I thought that they had made the biggest mistake and they were going to love me because I was going to show them that the right side view actually belonged over on this side and the top view actually belonged up here. Well, much to my chagrin and embarrassment, I found out that, in fact, in Finland, like the rest of Europe, they use a first angle projection, and no, their drawings were not wrong, and no, as a 19 or 20-year-old, I wasn't going to come into this company and set them all straight. So they set me straight, and I learned about first angle projection. What's interesting is, as I worked there over the summer, I got better able to understand, and I started to see the first angle projection. And then promptly when I went back to school and had to switch over to third angle projection, of course, my brain was still calculating or seeing things in first angle projection. So there was a little bit of a period of transition of getting accustomed to one or the other. But so that's my little story. Suffice it to say, again, that we're not doing any drawings in first angle projection. Fusion will do that for you, and if you're interested, you can play around with that. What you would have to do is use and we'll talk about this when you look at the drawing videos, but you would choose a European standard. So instead of the ASME standard, you would choose the ISO standard, and then it will automatically generate the first angle projection views. All right. So let's finish up here. We just got a couple more slides. So there are symbols to help people identify whether they're viewing an object that's in first or third angle projection. So first angle projection, this is the symbol that you would see typically in the title block showing the projection. And the way this is developed, notice we have a kind of a truncated cone, right? Here we have a cone. And so in first angle projection, what would be the left view over here is shown on this side. So we have a visible circle here and a visible circle here from what we would see from this vantage point. So that's the symbol for first angle projection. For third angle projection, again, we have the truncated cone, but the left side view in this case is developed from the left side of this cone. So again, this symbol, you would typically see that, and in fact, you can pretty much see it in a lot of drawings if you look online. You can see that in the title block. All right, so that's it. That's the first lecture on orthographic projection. I will see you in the next lecture, which I believe is section views.